I am kind of trusted with the task of covering so-called continuous valued random variables and their information associated with that, so as to enable Professor Benzel cover the rate distortion and other applications. And also you will see that many of the things that I say or what we discussed today will be used as the breadboard or the kind of things where Professor Kramer will later test his ideas on. So in that sense, this is really application wise very important to validate and understand many of the concepts that you learn in the information theory course. So please feel free to stop me in case you have a question, something that I am jumping over, etc., because my plan is to pack some 10 lectures into 2 hours and give to you, but I am sure that the week ahead can be more challenging. So I won't burden you, I will kind of give you the right point and then stop and move on. Okay, what we are going to do is that we are actually taking what is known as a Riemann sum approach. So Riemann sum approach is the simplest way. When you don't know what to do with anything, you just take simple things, add it up, get the answer and say that, look, I believe this is correct. So this is the approach that we are going to take on many contexts, not just in so-called entropies and things like that, but also in practical applications we will do this Riemann's approach. Okay, so I need some background recap from the previous lectures. So this I made before I came here last day, so I actually made this. So this one says that, okay, you should know the capacity of a DMC is a supremum over all input distribution of Ixy, where Ixy is given by this formula out here. So you are familiar with divergence. I should also say that, look, I also need some background on signal systems and probability, signal systems, Fourier transform, convolution, etc. I hope anybody who is from mathematics or not from electrical engineering, computer science, are you familiar with this Fourier transform and things like that? Okay, so I will try to just mention, you can refer it and but if there is a specific question, stop me, we can answer that. You are also from CSE. Okay, so this mutual information is given by this particular formula. This you might have seen already. It is a divergence between the joint distribution of xy and the marginal distributions px, py, product of the marginals. And there are some ideas related to how these functions behave with respect to px and py given x. In particular, what we know is that once I fix this input distribution and then look at this quantity, it is convex in py given x, and if you look at this axis where you fix a py given x and look through the px's, then you will see it is concave in px. If you do not know this, do not worry, I will not use it much, just to as a backup, but if you do not know it, you have to know one thing, that log x is less than x minus 1. The rest of the things all we will derive by just one equation, if at all you are confused about that. All I am going to use is log x is less than x minus 1, where the base is e, the natural base we are talking about. Okay, so now just to warm you up, can you name any two 20th century gadgets which is of most importance or which is very important in the 21st century? If you think about the most important gadget that many people will put their weight on, this particular one here, which has changed humanity in ways that we could not imagine. It is a bomb, or the associated formula that has come up with, E is equal to mc square. If you look at it, this formula was invented and later this bomb was discovered, as opposed to many of the other places where the engineering happens first and then you come with an explanation. The second biggest one I think is the mobile phone, if you look at the gadget, and it has a very kind of similar origin. If you look at that, it has also followed a set of formulas, and if this is the fundamental formula that you have learned from Shannon, and then there is a particular application of that formula into this kind of setting, which is the formula which is written here. It is called the Gaussian setting, which we are going to cover today, and this gave rise to the mobile revolution that we see. But a key difference is that perhaps writing down this formula, Einstein was not aware that you can make the bomb, or it was not meant to be making the bomb. In fact, he was against the idea of making the bomb. Whereas Shannon's ideas, all these formulas, he had a very clear vision that it is all leading to this kind of things. In fact, if you look in the reverse side, these formulas were governed by this application. That is a story perhaps not told in textbooks, etc. If you look at this, this is what Shannon's 1948 paper has come up with. This is a model from the paper there itself, right. Many of you might have seen this model. This model has a very nice symmetry, it is very cute. At that time it was considered very novel also. Now we think that, oh, it is very natural. The obvious things that there is a source, transmitter, receiver and destination separated by a noise source or a channel. A very inherent symmetry in this. But what is very, very key in this that people do not spend attention is that there are these two words here, message here and message there, right. So, what it says is that, look, the message is common to the transmitter and the receiver. In other way, the receiver should have the message. This was entirely different from the philosophy that people used for communications till that time. Now, I want you to hear it from the from one of the pioneers in the field itself. So, there is a small video that I put here. You can just listen to him. The audio may not be that high because my computer's speaker is not that great, but if you give your ears a good stretch, you can actually hear what is going on.
Shannon worked for the telephone company. So one of the first things that they figured out as a result of this is that you probably shouldn't just make a telephone line longer and longer and longer and put amplifiers in the middle of the line. Pretty soon the signal starts getting smaller. And so eventually you have to amplify. You have to make it bigger again so that the signal can move the next stretch. But every time you amplify the signal, you amplify all the imperfections that got into the signal, which we call noise. And pretty soon, all you had was noise. That led Shannon to a fundamental rethinking of the way telephone conversations.
So what you can see is that the standard communication, I can say louder what Jack Wolf was saying is that if you do analog communication, you send something, you may not get back what you sent, you only get a distorted version of that. And if you try sending it again and again, pretty soon you will end up with just noise and then it will be useless. Whereas Shannon's idea was of digital communication. So, in fact, that is how digital communication originated, that you start with a message and you regenerate that message and you repeat the regenerated message, right. So, this is the idea and it changed the way we look at communications and it changed over the last century so many things that you are seeing. So, what he did was to model that, he took that telephone line and he imagined that, look, I have to send discrete messages from this side to discrete messages on this side. So, I have some continuous signals available to me, xt is sent, yt is received. So, this is the analog part. So, I have to push data through this analog part. So, he said, okay, let me take a very natural discretization, let me just sample the signals and come up with a discrete model and try to see how much data I can push from this side to this side. So, what is the rate of communication through this particular channel under discretization? And he came up with this formula, which is the discrete AWGN capacity. This is half log 1 plus SNR. So, SNR is the signal to noise ratio. There are some extra implications and extensions to this. You can find in Ash's paper and Weiner's paper how to go to non-band limited functions and a lot of other things are here. But essentially he came up with this magical formula which kind of governed, dictated the way communication has evolved on all this time. So, our main plan for the rest of the 2 lectures is how to understand this formula, how did it come and where can we apply and all this. So, we will kind of familiarize ourselves with this formula which is of central use in the lectures which are coming ahead of. In particular, what we know is that this particular number is an engineering quantity. It is derived under a particular kind of signaling assumption, sampling, power constraints. A lot of practical assumptions are made before deriving this formula there. So, it is indeed a practical number. It is not just a theoretical number. We have to operate near this number, near capacity operation is the optimism behind this formula. So, people go ahead and keep deriving these formulas, applying this, coming with new ideas, etc., without even worrying about can you do this. That is because of this optimism that one day you will be able to get there or not, and we are close on the heels of this formula. So what our first part of the talks, we will focus on the practical aspect of why this formula is important, or how did this, where is the origin, what is the engineering behind getting to this formula. And in particular, we will talk about band limited communication, discrete time models, coherence, bandwidth, and I will show some demos also if you are interested in engineering application. This uses GNURADIO, which is a popular platform to demonstrate communication applications. How many of you have heard about GNURADIO? Okay, good. So I will show you that. It's a very useful thing we use for all our purposes. At your colleges, perhaps you can also use it. It's an open source thing. And then the next part is where I focus on the tools and the techniques and the mathematical aspects of it. And fortunately, we will get a good idea of what is known as mutual information, continuous valued entropy known as differential entropy, some of these isoperimeter relations which helps you identify what is the best way to communicate in channels, and last the capacity of the additive wide Gaussian noise channeling. And the third part is about extensions to various systems. I am not sure whether I will reach here and spend time on that, but I will at least cover some of that, right. And if you are interested, we can also spend more time in here trying to make very intuitive connections between so called Boltzmann's entropy, Shannon's entropy, etc. But these are like intuitive. If you like to learn that, stop me at that point. We will not go to the extensions, rather we will discuss more about this things. Okay, shall we go? Yes. Okay. First thing, how to model the channel or the medium that we have. So think about a transmission line. So Shannon had a telephone line, and he tried to find out how much data can you push from one end to the other side, or what is the rate of communication. So the way to model that is that you can think of all the effects that are impacting us, the physical effects, and take like, oh, we are really looking at the linear effects that is causing that is affecting the propagation of waves from the transmitter to the receiver. So we put everything together as a lumped circuit RLC. Right, and then we have an output, there an input, then we can say, okay, what is the effect of the input on the output, and then we will write down the model for yt, that is a received signal, in terms of xt, which is the transmitted signal. This is Shannon's idea as well. But the moment you take such a linear circuit, you know that all that is there in the circuit is governed by what is known as the frequency response of the system. At a frequency, how much is the output is what the frequency response says, right. In a way, in some sense, is a Fourier transform of the impulse response that we are talking about. Is it clear? So in the transmission line, what is allowed to us or what is given to us is some bandwidth beta. So there is a carrier frequency around which there is a bandwidth beta, and you can communicate in this allotted band, right. That no, this is some function. Sorry, it looks like Gaussian. Some function. It can go up, down, and things like that. I only showed the magnitude of the response. Yeah, it is unimportant. So sorry. Amplitude. Yeah. So in a way, it's unimportant whether it looks Gaussian or looks some other circuit here. Okay, some picture. But what you have is that. Oh, by the way, why is it symmetric? So why is it symmetric? Yeah, so of course we are trying to push real energy and an antenna out there pushing at the real vibrations of the electromagnetic. So we are talking about real system. That's why I drew it as magnitude is symmetric with respect to frequency. So now if you use a bandwidth beta here, then I can generate a waveform which has bandwidth beta and then push it by multiplying with a carrier, and I will send it through this particular part of the spectrum. What will happen at the output? At the output, this input response will get multiplied by the h of f. So we can then compute the effect of this propagation here by simply looking at what is the impulse response of the system. So let us understand impulses. So if I have x of t and I have an impulse, so the representation means that you get x of t as the output of the system. So impulse is something which represents that you leave it unchanged, you put it on the other side of the thing. Right? It's a symbolic representation we are talking about, right? It's no function that we are talking. It's a representation. If x of t signal has a band of a Fourier transform x of f, then this picture here means that x of f gets multiplied by h of f and you get x of f back. This is the Fourier transform I was talking about. This you can connect to you can connect to that, right. So, because essentially we are saying xt convolved with this response is same as xf multiplied by this hff equivalent to. But what is even cuter is that if I do not use this, for example, I use the same system, but the inverse of this hff is actually what is known as a sinc function. Here it is an impulse, here is a sinc function, but both produces the same output, right. So, the band limitedness somehow plays a game here, that impulse is not really an impulse, it is the system here is also an impulse effectively, right. And this is a key modeling thing that we can use actually to simplify a lot of the models that is out there in wireless or wireline communications. If you look at our example here, there is a RLC and there is some part of the response. So, I took the linear part of the response from the previous picture. If you just want me to go back, here is the kind of the linear part. So, to easiness to draw, I just took that part, and then xf times hf is y of f. Is all these things are clear, right? This just linear systems ideas, how to model a wire, that is what we are doing. We can do wireless just like this. The problem with this model is that Shannon wanted to communicate messages from this end to messages to this end. Now, this representation here is pretty much a mess. The reason being that your x of f, whatever input signal gets convolved with your frequency gets multiplied with whatever the response is, and then you get the output. In time domain, it is equivalent to the x of t getting convolved with the inverse Fourier transform of this. I have again drawn a representative picture, this is not true, but some representative picture. The problem now is that the x of t will react with this and y of t will come out, and if you look at that, there is a continuous reaction, in the sense that every x of t, there is a continuous combination of different points of x of t which is generating the output. If you look at the output, it is a convolution of this with x of t, which is given by an integral. The integral means that you mix up different parts of x of t, in fact a continuum of parts. So, you want a message is contained inside this x of t, y of t is now all messed up, all convoluted things of the signal. So, how do you get back the message is somewhat a very tricky thing, because you do not have a set of linear equations or something to solve. You have integral equations, and now you have to solve it to get your x of t. So, this was something of a problem mentally and mathematically to get back what the message was from y of t, even if you do not have any additive noise, but just a system, a transmission line like that, right. So, the transmission line mixes things up, or intersymbol interference is the word that if you want to use it. Whatever I transmitted earlier can affect what am I receiving now, and all those things as a problem. So, how do we model this one? So, I will show a very intuitive model how to approach this. For example, if I add two pictures here, like I added this dotted pictures here, will my output change? What do you think, Jibu, what do you think? The output will change? It will not change, because the product is 0 everywhere. So, the product comes out to be this. So, if that is the case, well, why not let me just repeat it completely through the entire axis. So, then you get what is known as a periodic frequency domain representation here. Oh, then we can know what is the Fourier inverse of this, the generalized Fourier inverse of this, because if you repeat in a frequency, you just sample in time, right. So, what happens is that the same effect of a continuum of system can be generated by a set of discrete impulses. The same output, the output is exactly equivalent to what is coming through the system. So, now we can do the thing, look, I have a set of linear equations to work, because this is a linear combinations of the input. If you can see, that is exactly the linear combination of the inputs that you get. So, any continuous time, linear time invariant channel, you can just break it using band limitedness, you can just break it into a number of discrete paths. But once you have a discrete paths, look at that, these are just linear equations in terms of signal, you will eventually be able to solve, provided you have enough number of observations, right. Is the idea clear? Right. So, this is one of the first modeling things that we can do. In fact, I have a representation here, let me just go to the next and show you. So now I just do a small demo to just to show you that look, these are very practical things. It's not just theory that we are talking about. In fact, you can put it on, make a wireless transmitter in no time if you have access to what is known as a software radio. So here I am going to illustrate with whatever I said with GNURADIO. So what we have is a source, and we just send it through a modulation here, right? And the computer science people, the modulation may be new. Is it new? Yeah, okay. So what we are doing is that we are taking these messages and converting to symbols which I can push through the system. In particular, what I am going to do is that I am using what is known as here so-called PSK or QPSK, where I take two bits and send out a real value. If I get 0 0, I will send a complex value of 1 plus j. 0 1, I will send 1 minus j. 1 0, I will send minus 1 minus j, and 1 1, I will send minus 1 minus j. So you have all the, if I said correctly, you have all the combinations of the thing, and you can just push it through. Here is some kind of a digital clock. This is no need to worry about this block. And then I will push it through some kind of a channel, and then here is a receiver, and I will show you the output. That's the idea. So here is the idea. So I written it down into, this is called GNURADIO. So it's a software radio. This is completely run in the computer. So, but you can as well connect it to a dongle and have wireless systems made in no time and so on. Okay, so I'm going to run this. Then you will see what's happening. Okay. So as I said, it's QPSK means 0 0 is one of this, and 0 1 1 0 1 1. So there is a amount of signals coming through. So I'm just looking at the receiver, what they find out about the transmitter. And here is a response of the channel that I have put in the system. So its output, how does it look? If you look at it, here is like, what you have to concentrate is on this minus 10 to 10, which is a fairly flat region here. So which essentially means that the input is coming out exactly as the output, right? If the channel or the medium creates variations, then you will not see this flat line here, because it will go up and down, just like the picture I showed you in here, just like the picture here, it will go up, down, etc. Okay, sorry, this is okay. Now what I am going to do is that, okay, here there is no noise. I can add noise, so I just press this knob here, so it will add noise. Now I can see what happens. So it will, each point gets distorted by the addition of noise, and then you will be, it will be difficult for you to tell which point you are in this detection problem. So this is the effect of noise on the system. But what we are more interested is in the effect of okay, let it settle. So now I am going to distort this portion. You should see what is happening into this system here. So let me just distort this. So you can see that distortions here is creating multiple points onto this side. These multiple points are called inter-symbol interference, because each symbol is interacting with the previous or the next symbol. So there's 4 points coming because this guy is interacting with this and himself. So this 4 points comes into picture. So if you distort this path more and more, then you can see that things are all lost, and you'll be able, very difficult for you to get back your things. So the whole problem in this communication, wireless or wireline, etc., is about looking at that kind of an input and how to figure out what was that transmitted signal, right? And if you add noise, now you can see all kind of bad things happen. There is absolutely no way to say what it is. And but other things typically communication engineers do not worry about are also a big problem. For example, there is something called frequency offset. You can just, if I just put a small frequency offset, you will see in no time everything will be gone. So this problem we kind of put under the carpet, saying that look, we can somehow work it out and things, which is true, but under the kind of abstraction of you can synchronize, you model noise and the channel, and then we have to get back the signal. So that's a challenge. That's how you can model the system. Okay. Now let's, any questions at this time? Which one are you talking about? Yeah, no, that's this relative amplitude, don't worry. It's relative. So you can think that this is a noise floor, this is somewhat so many dBs above it. Yeah, that's correct. That's correct. Okay. So let me just, yeah, please, any question? Yes, Jibu. Ah. Ah. Ah, very good. So okay, so good. So let me just close this and go back to that question. Yeah, very good. Good observation. So Jibu is pointing out that, look, I used here a supremum, whereas Professor Banerjee or Professor Bensel might have used maximum in this case. I could use maximum once I work through this and show you that, look, there is an associated nice concavity in this, so that there is an answer within this set. So this is a convex set, and you are guaranteed that the objective is concave, so there is an answer inside, then the supremum will indeed become the maximum. So I can use it if you already know this, yeah, I can come back and show that sup is max, right? But without this, I cannot claim that it is a max. Yeah, convex set and a concave set of probability distributions, and Ixy is concave in Px. Concave functions in a convex set will have a maximum. Okay, so this is mostly the engineering side of it, so that to get you excited and say that, oh, these are all practical stuff what we are going to do. Now we will slightly go to the math side of things. Okay, here is how Shannon did it. So what Shannon did was he discretized, and there are m messages to send, so he will form code words. These are block coding. You have already learned it, as I think you have already learned it. So for each message you send out a code word, which is a vector, and when the vector passes through the channel, each symbol is getting added with Gaussian noise, and this Gaussian noise are we assume independent Gaussian noise, and or so called white Gaussian noise, and the y is nothing but the sum of the x and z. So you make n observations for a block, and from these observations you have to come back to what messages that you have transmitted, right? So for example, if you get all this cream region, then you may say that, oh, it's the first message that's being sent, or it corresponds to this code word. All this one you can say this is this message, all this one you can say that it's a third message, and so on. Am I making sense? Okay. So this is what's the best decoder to go back from here to there? Look, you have to decode. I'll observe this. I have to tell what is here. So what is the best decoder? Depends on the objective. The objective here is that we want to minimize the average error probability between what is sent and what is decoded. The message which is sent and the message which is decoded, the probability that they are not equal, we want to minimize that. So what is the best decoder minimizing the average error probability? It is in general it's a map decoder, right? But here, since we assume in information theory and all the discussions you might have seen that we assume uniform likelihood on the messages, then its maximum likelihood is the best estimator, and because it's Gaussian, the maximum likelihood simply breaks down what is known as minimum distance decoding. You take the y and find the x which is closest to it, and then declare that is the message. That's the best decoding, or you cannot beat it. That gives you the minimal error probability. Okay, is that clear? We can derive all these things also if you are. I'm kind of assuming these things are clear for you. So what are we? We got a y. So let's call this as, let's say we got y bar. We got y bar. Okay, and I'm going to pick the x bar such that this is the max. So I have m x bars here, first vector, second vector, etc. I'll pick the one which maximizes this, right? But y bar is nothing but x bar plus z bar. Z bar is a Gaussian vector, right? And they are IID Gaussian vectors. So you can say that this number is kind of proportional to e power minus the distance between, right, and then actually there was another constant, let us put C2 here, right. So, what you want to maximize means you want to minimize this. So, minimize means that you have to pick the one which is the closest to the y, because the L2 distance we are talking about, correct. So, we take the L2 distance and declare the code word, and then this is the best decoding that we can do. Now, Shannon also said that look, you cannot just use an arbitrary high power onto this. You cannot simply choose signals which are like very, very huge and big, but you should have a common sense constraint which is called the energy constraint or a power constraint. He said that each code word, if you sum up the energies, it should be at best n times p, or n times p you can think of E as the energy. The total energy should be at best E, so it should be less than or equal to for the actual constraint there, right. So, this is called the power constraint. If you look at it, if you take 1 here, 1 over n summation of xi square, this will, if they are random, it will behave like an expectation, right. So, Shannon said that okay, why not, let us put a constraint, right. This is an input constraint that expectation of x square less than or equal to p, okay. That is what that's what that constraint is. Now, we can go back and maximize use our formula, maximize Ixy subjected to the constraint that expectation of x square less than or equal to p. This is a very natural, again an engineering constraint that we need, so that our devices operate with a finite energy. So, in n uses of the of transmission, I can spend at most E energy or p power to send it. Okay, here is an intuitive approach under these conditions how to derive Shannon's formula. We will have a much more rigorous approach as we go on. So, this is an intuitive approach here. So, you have y is equal to x plus z. So, you have to think of this decoding, these are decoding regions, and all these points are closer to the first code word, because the decoding is the closest distance, right. So, all these guys here, all the vectors here are closer to the first code word, all these are closer to the second code word and things like that. So, we can divide the whole region into m such decoding regions. Here is the code word, and here is all the outputs which are closer to that code word. Here is another code word, here is all the outputs which are closer to that code word, right. But what we know is that y is x plus z for a vector z1 to zn, if you sum up the powers, they behave like n times sigma square. This is law of large numbers. So, there will be a plus or minus O(n) term here. So, we are ignoring that, and we are saying that okay, roughly the power of this noise vector is n times sigma square. Is that clear? So, what it says is that look, I can compute the volume of this sphere because its radius is n square root of n sigma square. So, I can compute the volume of the sphere. Our total power is p plus sigma square. P is the input power, sigma square is the noise power. So, you can find the place in which a vector for y will lie is inside this big sphere, and for each code word sent, the output will be in this particular small sphere. So, total how many spheres can you pack is the question. That will tell you how many messages you can choose. If you have more space, you can put more messages, that is idea. And so, you can use, since you know the radius to the power of n, the constant radius power of n will be the volume. And so, the bigger sphere's volume divided by the smaller sphere's volume will give you the number of spheres that you can pack, or the number of messages. Log number of messages will give you the number of bits that you can push through the system. And so, this number will evaluate to n over 2 log 1 plus p over sigma square, and this many spheres you can put in n transmissions. So, per transmission you will have half log 1 plus p over sigma square. So, this is a very intuitive derivation, but it is not very correct. I should tell you that it is intuitive, it makes sense, because high dimensional packing is not a well understood topic. There are a lot of caveats in this thing. Though Shannon, one of his papers, makes a very precise calculation using spherical caps and ideas different from this to validate this formula. It is intuitive, it is a plausibility argument, but it is not a very precise argument, right. That is why we need actually a precise argument to show that indeed this is the rate that we can say. Okay, any questions? Okay, so this is to give you a big picture of the stories that what we are trying to get to. Now I will kind of zero in and go to the maths and associated aspects that we can do. Okay. So yeah, so you can see P over sigma square I have written the SNR, and so it's half log until SNR. The unit I will explain as we go on. Okay. Now it's module 2. Though the first part was more of a warm up for you to see that look, this is all important stuff that we are talking about, and there are a lot of engineering significance, etc. Now we will go to the mathematical aspects, which will kind of help us derive this formula or even find applications in other places. The engineering is very specific to a particular problem that we looked at, transmission through a wire, etc. This is much more abstract and general that you can apply to a wide variety of problems. Okay. In particular, we will talk with start with mutual information, move to differential entropy, and then derive what is the capacity of the channel. Okay. Given this system, y is equal to x plus z, expectation of x square is less than or equal to p. What is the capacity? Capacity is now, as Jibu pointed out, it is a maximum over px of expectation of x square less than or equal to p. Ixy you can derive. But then the question comes, what is Ixy? We have not studied so far what is Ixy. You only studied Ixy for discrete random variables, right? All the typicality, you did typicality and things like that. So, all for discrete random variables. How do you now work for continuous random variables? First of all, we are not interested in entropy of a continuous random variable just like that. We are interested in the mutual information, right? Or capacity. Let us say we are interested in capacity. How do you find the capacity, provided we know the discrete answer? So, I have a continuous system, y is a continuous valued system, y is equal to x plus z, and I want to find some idea of capacity. What will you do? Prashant, what will you do? The first approach. You have y is equal to x plus z. You know a lot about Professor Banerjee has shown you yesterday how to compute capacities for various channels and systems, etc. So, you know how to compute for discrete. Suppose somebody tells you there is an algorithm that somebody gives you, here is how you compute the capacity for a discrete channel, a discrete valued channel. Now, I give you a continuous valued channel. How do you adapt your theory to the continuous valued system? Density functions, everything is available, but see, suppose you have a computer and you want to store an audio file, what will you do? Sorry? Exactly. So, you quantize, you use a quantize and an ADC, right? Sorry, ADC with a quantizer. So, it will give you a finite bit precision version of the thing, then you store it, hoping that that will kind of store all the information inside that. So, that means as engineers you know how to deal with continuous signals. You can appropriately quantize them and say, oh, now I hold the discrete in my hand and play with it. That is idea. Okay. Now, using that idea, can you compute the capacity of a channel y is equal to x plus z, where y, x and z are all continuous valued? In audio you know how to do. So, how do you do here? Same idea, you just quantize. You have y, you have x, you just quantize all those parties and say that look, I may lose something in precision, but still I work with quantizations, and in quantizations I know the answer. I just have to apply the theory that we have already learned. So, at a first cut you know the answer to all the continuous valued questions. It is a brute force approach, but you can do that using the old theory that you have learned. We are just going to give an extra tool to make it a more streamlined computation. That is all we are trying to do. There is nothing new that we are going to do. We just, the same old theory, we will just polish it a little bit so that you can quickly compute those quantized computations. Okay? In game? Okay? Fine. Okay. So, let us go about that. So, here is the thing. You have x and y according to a density function fxy. So, I am kind of thinking, taking that they admit a density. And what we take is that we take all the partitions of x and y. So, I took rectangular partition so that I can then talk about a marginal of x and a marginal of y, right. So, I partition the x space, I partition the y space and then say, oh, this q is a partition, I can compute the mutual information between x q and y q, which is nothing but h x q minus h x q given y q, where h x q is nothing but the summation of the probabilities log 1 over probabilities. Standard discrete entropy. So, using discrete entropies I can find this formula here. I can do it for every partition. So, I will take the supremum over all partition. As Jibu can again see, I am using supremum here because the limit of the partitions I do not know whether that is within the thing. Okay, fine. So, we use the old idea, we just know no need to reinvent the wheel, we just use the old shut and just press it and use it again kind of idea. So, we get I x q y q, we take the supremum over all partitions and just call it as I x y. So, for each distribution I can just do that. So, I can also maximize this thing in principle, I can do that, right. But is there a cleaner way to do that than just this dirty way of picking each piece and doing that? Turns out yes, and that is motivated by this thing called, if you take nested partitions, that you take first one partition of x and y, take another partition which is finer in the sense that using the new partition I can create the old partition, right. So, I will take more and more bit precision, that if you want to call it that way. Then what happens is that the mutual information can only go up. If you partition finer and finer, the mutual information can get better and better, or it cannot decrease, that is why we use the word non-decreasing in K. Is the idea clear? Take x and y, you quantize and you compute mutual information. If you quantize further, finer, you can only have your mutual information go up and up. Okay. How do we prove it? Let me ask suggestions, we will prove it then. Yes.
It's like if we have finite number of points, then because of quantization, then we cannot cover the area. It's like
correct. That's correct.
We are trying to approximate the area of something.
Yeah.
But as we do finer partitions, then we will reach closer and closer.
That is very correct. So, which essentially explain that the supremum is somehow is the answer that we are looking for. But this is all it is okay to put intuition into it, but then there is a straightforward math that you can work it out, and that will give you intuitions which are more powerful than the ones you started with, right. So, just write the equation that suppose I have partition q1. So, I x q1 y q1, this is discretization of x, discretization of y by some means. This is nothing but the discrete entropy of the first party minus the discrete entropy of x q1 given y q1, definition, nothing else we are using. Now, what happens, I want to say that if I have partition q2, I will get this thing better. What do you do? I push, yeah, yes, please. Sorry? No, not 0. I want to say that I will get better by putting q2 here. So, what I do is I first simply put, instead of q1 I put q2, but q2 is a better partition. So, q2 contains everything about q1. So, I have conditioned more, conditioning reduces entropy, and so that means this number has come down, this number stayed the same. So, this number will be less than or equal to that. Is that clear? So, I have more, I have much less entropy when I give more information about this y on this party. Okay. So, now this is nothing but I x q1 y q2, and I just do the opposite, h y q2 minus h y q2 given x q1, you get x q2 y q2. So, it is a simple idea, extremely simple idea, just do it 2 times and you get the answer to that. So, as you partition finer and finer, your entropy, or sorry, mutual information goes up and up. The only entropy we are talking about is the discrete entropy here, that sorry, something that we already know. Is the idea clear? So, mutual information goes off by finer and finer, which gives us a clue of how to handle these things, because I just have to get finer and finer, that is it. So, we can do a very uniform quantization, or so called Riemann's idea of the thing. We will just do uniform quantization, because by finer and finer we can reach as close to the original as possible, right. So, this is the idea. So, essentially it is Riemann's idea. So, you want to compute IXY or HX, XQs etc. for various quantization. So, x for example has a density function that I have drawn here. So, this is a uniform quantization of delta quantization. So, what it says is that the probability of x takes this value xi is nothing but the density function times the width, essentially the area of the shaded region is fxi times delta for uniform quantization. So, the probability that our original random variable x falls into this interval is given by fxi into delta. Is that clear? Clear for all? Right. So, now we using this we can compute probabilities and we can keep computing discrete entropies because we know the probabilities, right. So, then what we do is that for all integrals we will do kind of a Riemann sum approach. Can we approximate these sums by Riemann integrals? And in all the talk or all the class we will assume that such limiting sums exist, because every time I write it I have to make a discretion whether that integral or the limiting sum exists or not is a question. We will take that they exist, but it can be possibly plus minus infinity, that we do not limit, but it should not be infinity plus infinity or infinity plus minus infinity. Those kind of operations between infinities are not allowed. Okay. Things can go one way to infinity, which is fine. So, what we have is that, see, we have, let me just draw some picture. So, this is easier, right. This is our fx. So, I quantize. So, suppose this is one quantization and this we said is the unit is delta, uniform quantization is what I am taking. So, what is the probability that your x falls into this interval, right. For small enough delta, this is approximated by fx. So, this is, let us say this is xi. So, this is f of xi times delta, right. So, it is the area under that thing, that is all I am taking, right. So, you can use uniform quantization for each point, ith point you give fxi times delta, because we know the density function, that is a probability of that. So, now using that you can compute the quantized, let us say x, this is a quantization of x, then this number will be that is the number for all I in integers minus infinity to plus infinity. The ith one stands for the ith piece of the quantization. So, now hx delta is nothing but pxi log pxi, where pxi is a probability of falling into that ith piece there. Okay. This is the definition of discrete entropy. But pxi is approximately fxi delta. When delta is small, this is a very accurate assumption, you can take equality there, but otherwise it is an approximation. Pxi is fxi delta. So, I find fxi times delta log 1 over fxi times delta, sum over all I will be hx. Okay. Now, what I can do is that, okay, I will just write this as log AB is log A plus log B. So, I will just write log fxi minus log delta onto this side. So, this is what my discrete entropy of quantization is, approximately this much. Okay. Now, what I can do is that I can compute hx delta given y, conditioned on y, it is not y delta, it is y, you can put y delta also, no problem, because the definition of conditional entropy is that for every y is equal to little y, I will find hx delta given y is equal to y, which is based on the same formula. So, this summation here is simply given a particular little y, the same formula that I have used. So, given a particular y, then I integrate over all y. It is expectation of x is expectation of x given y, the expectation of that, right. So, condition on a particular y, I will evaluate the thing and then I will integrate over all the probability of y. Is that clear? Anybody needs a derivation or anything of the form? For each y equal to y, we will compute this entropy, then average over y. That's all we are doing. Is that fine? Fine. Yeah. So I did not. That's why I put an approximation. I know where I put a delta 2 going to 0 there, but delta is small. Think of it small, right? Okay. So that is why I did not work directly with that, but rather I wrote both the formulas with log delta there. So delta is small, so this is an approximation of this form, so the approximation holds uniformly holds. Now what I am going to do? I am going to compute I x delta and y. So I x delta and y is nothing but the difference of this quantities. So for any delta, this log delta and this log delta will cancel. So I will end up with the difference of this and that, right. That is why the delta going to 0, because I first subtracted then took delta going to 0, so that the delta is not coming and hurting me, okay. But how about this quantity here, that without the delta, what is this quantity? No, this entropy. So this is exactly what is the Riemann's formula, Riemann's sum is. So if you have, so suppose you have a function, let us say fu and u, and you want to find integral fu du from, let us say 0 to t, some t, right. So what you are going to do is that you take this point here, you are going to add up all the things, right. So essentially what you take is that fui, if this is delta, that is the area, and then I sum over all I, appropriate I get the thing, right. So if I take the width and then the height and product, compute the area of the rectangle, adds it up, it will effectively, if delta goes small, I will get this equation. This is the Riemann's summation. Same thing I am doing here, there is a delta here, fxi log 1 over fxi is my fui there. So I am just summing over all those things, it will simply go to fx log 1 over fx. Is the idea clear? Right. So then I get a formula which is much neater, cleaner, it does not have any clutter of quantization, nothing. Simply saying that I have to take delta go to 0 to get into this limit, but this delta is taken care, the subtraction is gone there. So this quantity here is, we call it as the h, little h of x, it is called the differential entropy. This is the conditional differential entropy hx given y, right. So it's quite neat, because now you can just compute this integral, hx minus hx given y will be the mutual information ixy that you are looking for, because delta goes to 0, that is the finest partition that you can get, okay, and mutual information goes up with partitions. So you eventually you will tend to this answer. Idea clear? So that is the idea of differential entropy. We can give very strong physical interpretations to this entropy in comparison to differential entropy also, but maybe in the break or a little outside, if you have questions, I will take it and I can give you much more intuitions. But as in the class, perhaps I will try to go more with these equations than the intuitions, because it will be helpful for you to know these equations in Professor Kramer's and Professor Benzel's classes. Any questions at this time? Okay, so now let us now look at it from the other side. So I am going to, here I connected the discrete entropies to the continuous entropies. Let me look at, so that your idea is completely thorough, let us come the other way. I will start with differential entropies and then try to, so this is called differential entropy, discrete entropy and differential entropy. This formula gives the differential entropy, it's a conditional differential entropy. So that is why it is a limiting entropy under uniform delta quantizers, but you should think that I have factored out this log delta of the picture to get this formula correct, right. So you should see that, but we can make strong connections. Let us see. Here is an hx distribution given to us. H of x is nothing but integral fx log 1 over fx dx. So I wrote it as two parts, the blue colored one and the red colored one. So instead of quantizing, I just quantize into two, everything which falls into this blue color and everything which falls into this red color. Let us see how we can connect the total entropy to the one of the red color and the one of the blue color and vice versa. That will give us a very strong intuition to work through any complex system, just like Professor Adrish yesterday showed you how to decompose things into channels where you can quickly compute. Same, that is again the reverse Riemann's idea, Riemann's analysis idea, the other is Riemann's synthesis idea. So what we do is we just look at this integral on the portion A, the A portion is the blue portion, B portion is the red portion. So So, you have the integral, same integral fx log 1 over fx dx, fx log 1 over fx. I put a line because I want to add additional things in the next slide, that is why I put a line and a bottom empty here. Okay, is that clear? It is just the integral split into two parts, and so that I can talk about the conditional entropy on the blue and the conditional entropy on the red, I will divide by the probability of being in this A. So, integral fx dx on this blue part, I will scale it below. So, I will put PA here, I put a PA there, so they cancel. Here also I put a PA there and a PA on the bottom. Same thing PB, 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 PB. So, you will get back the original integral. Now, we look through details what is happening. Fx by PA is fx given A. Conditional on x happens in A, what is the probability of fx is exactly this quantity here. So, we can see that PA times fx given A log fx given A, this will give fx given A, and this PA and this PA will come out to PA log 1 over PA, right. Similarly with PB, right. So, what is happening is that if you look at PA log PA 1 over PA plus PB log 1 over PB, it is nothing but the discrete entropy of its A or its B. So, if you have a switch which tells us it is A or B, this is exactly these two terms are the entropy of that switch. Is it A, is it B? What are these quantities? So, you have the entropy of the switch which tells you whether it is x A or B. PA times the conditional entropy of x given A, this is a conditional differential entropy of x given A. PB times the conditional differential entropy of x given B, right. So, it is a very intuitive way to write it, like if you have a division, it is the entropy of the switch plus, if you are in A, what is the probability of A times the differential entropy of A, probability of B times the differential entropy of B. In fact, we can put all of them together in one number. I did not write, can anybody say how can it I write it in two entropies? Is the question clear? So, here are three entropies, first one, second one, third one. Can you just write it in two entropies? Will tell me that you have understood it completely. Is the question clear? No. Question clear? No. Please stop me before, otherwise sometimes I may go tangential. So, please stop me. So, this part, is it clear what we are trying to do? We have an equation for the differential entropy, and from that we are trying to see what is the discrete components inside that. So, we kind of broke it down. This calculations are okay, right. So, we came up with this number here which says entropy of it's either here or there, that is binary entropy of that. I think you used this notation already, HB, B for binary. So, it is a binary entropy, it is simply the sum of these two terms, and this term here the integral is h of x given A. So, PA times h of x given A, h of x given B. So, PB times h of x given B. Now, the claim is that I say that this number, the sum of these two is what? It is exactly the conditional entropy of x given S, right. So, what we have come up with is that h of x is h p of S plus, not p of anymore, because it is simply entropy of x given S. That is what we have come up with, right. So, the discrete components were whichever, and then plus given a discrete component, what is the conditional differential entropy remaining on that. So, we can easily break it down into this. Suppose I keep on doing this, suppose I take into each rectangle here is a different portion, what will you get? So, I keep again breaking down this quantities further. So, you get that eventually you will go to h of x delta, that is the entropies of where you are here like that. So, the switch will tell you which box, rectangle box you are in, which is nothing but the quantized entropy of x plus the entropy of x given x delta, right. But if you look at that, what is the entropy of x given x delta? As delta gets smaller and smaller, all you have is that you have to tell x into a small interval between of size delta. That's all they are, right? So if we can, so this will go to some constant. If you continue uniform approximation, this will go to some constant. Let's call this as g of delta, because they all look alike. The distribution of all these parties are nothing but it's a uniform distribution in this thing as delta goes small, right? That's the idea of Riemann approximation. So what happens is that this number will go to a constant. In turns, next slide I'll show that this will actually go to log delta. So this is log delta. Okay, this is nothing but the formula we derived earlier. That's where we started from. Okay, that log delta is it's coming in the next slide. Okay, how do you get log delta? Okay, is that clear? So you can come one way or you can go other way. It's all connected very intimately with each other. It's very intuitive, but you have to work in terms of mutual informations. Do not put yourself in terms of entropy and try to support it with meanings. It can be done, but not using the tools that I've used here. So for all the Riemann integrable functions, uniform quantization is good enough, because you are going finer and finer partition. You come up with another non-uniform partition, my finer partitions will eventually subsume all of that.
But there are some problems with the uniform quantization. There is some slow polar distortion and all this noise will be there, not more. That if you don't follow the step size.
No, there are two aspects that we are trying to say. One is about representing x or some variable with certain fidelity, so that I will be able to tell back what it is. Now that you have to actually use the distribution, and uniform quantization may not be a good idea of the thing, right? The other thing is that you have to look at y and say how much you know about x, right? Now quantization, we are using it only as a tool to understand how much is contained, and we are only, in the end we converted everything to this integral here, no?
Yeah.
So now quantizations simply became irrelevant. Quantizations was a way to kind of dive into it, use the theory that we know, but we came out of the thing with a new concept called integral, which we can find everything out of it. So quantizations became irrelevant, but for all practical purposes, what we are saying is that if you want to think through, uniform quantization is good enough, because all we are using is Riemann integrals. That's what we are saying.